Today's lesson is called Glacial Transportation and Deposition. So far, we have looked at how glaciers form, how they move, and how they erode the land through processes like plucking and abrasion. Today, we are moving on to what happens to all the material glaciers pick up. A glacier does not just carve the land. It also acts like a giant transport system, carrying rocks, dust, clay, and even huge boulders across the landscape. Eventually, when the glacier loses energy or melts, it drops this material. This process is called deposition. By the end of today's lesson, you should understand how glaciers transport material, why glacial deposits are usually unsorted, and how landforms such as moraines, drumlins, and erratics can help us reconstruct the movement of past ice. Let's begin with the learning objectives. By the end of this session, you will be able to explain how glaciers carry material inside, on top of, and beneath the ice. You will be able to describe the process of glacial deposition and explain the formation of till. You will identify landforms such as moraines, drumlins, and erratics. Finally, you will link these landforms to the direction and energy of past ice movements. That final point is important. These features are not random. They are evidence. They help geographers work out where ice once flowed, where it stopped, and how powerful it was. Before we go further, let's go through the key vocabulary. The first word is deposition. Deposition is the process where a glacier loses energy and drops the material it has been carrying. The second word is moraine. A moraine is a landform made from deposited till. Moraines are often found at the sides or end of a glacier. The third word is drumlin. A drumlin is an oval-shaped hill made of till. Drumlins are shaped by the movement of ice above them. The fourth word is erratic. An erratic is a large boulder that has been transported by a glacier and dropped in an area of different rock type. These words are important because they help us move from simple description to proper geographical explanation. A basic answer might say, the glacier dropped rocks. A stronger answer would say, as the glacier melted, it deposited unsorted till, forming landforms such as terminal moraines, drumlins, and erratics. Before we focus on transportation and deposition, let's recap erosion. Glaciers carve the land through processes such as plucking and abrasion. Plucking happens when meltwater freezes onto rock, and the moving glacier pulls fragments away. Abrasion happens when rocks embedded in the glacier scrape and grind against the bedrock below. Over long periods of time, these processes can transform narrow V-shaped river valleys into wide, deep U-shaped valleys, also known as glacial troughs. High up in the mountains, erosion can create corries, arêtes, and pyramidal peaks. A corrie is an armchair-shaped hollow where a glacier begins. An arête is a sharp ridge formed when two corries erode back to back. A pyramidal peak forms when three or more corries erode into a mountain summit from different sides. This recap matters because the material that glaciers transport often comes from erosion and weathering. The glacier first breaks and removes rock, then carries it, and later deposits it. Let's ask a question. Why is it useful to understand erosion before studying deposition? Here's a model answer. Because the material deposited by glaciers often comes from rock that was first broken down or eroded by processes like freeze-thaw, plucking, and abrasion. Let's complete a quick progress check. Question 1. Which process involves ice freezing onto rock and pulling fragments away? Question 2. What is the name of the steep-walled, armchair-shaped hollow where a glacier begins? Question 3. True or false? A hanging valley is often marked by a waterfall flowing into the main glacial trough. Write down your 3 answers now. Try to answer from memory before we reveal the answers. Let's check the answers. Question 1. The process is plucking. Question 2. The armchair-shaped hollow is called a corrie. You may also see it called a cirque or combe. Question 3. The answer is true. Hanging valleys are often marked by waterfalls because smaller tributary glaciers eroded their valleys less deeply than the main glacier. Well done. Now we are ready to move from erosion to transportation. Imagine a glacier as a huge, slow-moving conveyor belt. A river can only carry material depending on its energy. When a river has lots of energy, it can carry larger material. When it loses energy, it drops the heaviest material first. That means rivers often sort their load by size. Glaciers are different. A glacier is a solid mass of moving ice. It can carry tiny clay particles, sand, pebbles, and enormous boulders all at the same time. A boulder and a grain of dust can move at almost the same speed because they are trapped in or on the glacier. So where does the material come from? Some material falls onto the surface of the glacier from valley sides. This can happen because of freeze-thaw weathering, where rocks are broken apart and fall as scree. Other material is pulled from the valley floor through plucking. Some material is scraped from the bedrock through abrasion. Over time, the glacier becomes loaded with rock fragments of many different sizes. That is why we can describe a glacier as a conveyor belt. It picks up material, carries it through the landscape, and eventually drops it somewhere else. Let's ask a question. Why can a glacier carry much larger material than a river? Here's a model answer. Because a glacier is a moving mass of ice that can trap and carry material of all sizes, whereas a river must have enough energy to keep material moving in flowing water. Geographers classify glacial load by where it is carried within the glacier. There are three main types. The first is supraglacial load. Supra means above or on top. Supraglacial load is material carried on top of the glacier. This is often rock that has fallen from valley sides due to freeze-thaw weathering or mass movement. The second is englacial load. En means within. Englacial load is material trapped inside the glacier. It may fall into crevasses, become buried by snow, or be carried inside layers of ice. The third is subglacial load. Sub means below. Subglacial load is material carried beneath the glacier. This material is dragged along the bedrock and can act like sandpaper, helping the glacier abrade the valley floor. These three positions are important because they affect how the material behaves. Material on top may simply be carried along. Material inside is trapped within the ice. Material underneath is dragged and crushed, so it can help with erosion. A good way to remember them is supra on top, and inside, sub underneath. Repeat that with me. Supra on top, and inside, sub underneath. Now we move to deposition. Deposition happens when a glacier loses energy or melts and can no longer carry its load. Unlike a river, a glacier does not usually sort material neatly by size. When a glacier melts, it can drop everything together. Huge boulders, smaller stones, sand, silt, and clay. This unsorted material is called till, or sometimes boulder clay. Till is one of the most important types of glacial deposit. If you look at river deposits, you often see sorting. Larger material is dropped first when the river loses energy, and smaller particles are carried further. But with glacial till, you may find a massive boulder sitting in the same deposit as tiny clay particles. That is because the glacier was carrying them all together in the ice. This makes glacial deposition very distinctive. So, if geographers find an unsorted mixture of angular rocks, clay, and boulders in a landscape, they may interpret it as evidence that a glacier once deposited material there. Let's ask a question. What makes till different from river deposits? Here's a model answer. Till is unsorted, with large and small material mixed together, whereas river deposits are usually sorted by size because flowing water drops heavier material first. Now let's look at one of the most important depositional landforms, moraines. Moraines are ridges or mounds of till deposited by glaciers. Their location can tell us where the ice once stood and how it moved. The first type is lateral moraine. Lateral moraine forms along the sides of a glacier. It is made from material that has fallen from valley sides or been pushed to the edges of the ice. The second type is medial moraine. Medial moraine forms when two glaciers join together. Their inner lateral moraines merge and form a dark line of debris running down the middle of the combined glacier. The third type is terminal moraine. Terminal moraine forms at the furthest point reached by the glacier's snout. It marks the maximum advance of the ice. This is especially useful evidence. If we find a terminal moraine in a valley today, we can say that the glacier reached at least that point before retreating. Terminal moraines can also act as natural dams. They may block meltwater and help form lakes, including ribbon lakes in glaciated valleys. So moraines are not just piles of rock. They are clues. They tell us where ice moved, where it stopped, and how much material it carried. Let's ask a question. Which type of moraine would be most useful for identifying the furthest point reached by a glacier? Here's a model answer. A terminal moraine, because it forms at the glacier's snout and marks the maximum advance of the ice. Let's now check the key terms. Complete the sentence using the word bank. Material carried on top of the glacier is called blank load, while material underneath is blank load. When the ice melts, it deposits an unsorted mixture of rocks and clay known as blank. Your word bank is supraglacial, englacial, subglacial, till, silt, terminal. Take 1 minute to fill the gaps. Remember, think about the prefixes. Super means on top. Sub means underneath. The completed sentence is, material carried on top of the glacier is called supraglacial load, while material underneath is subglacial load. When the ice melts, it deposits an unsorted mixture of rocks and clay known as till. This gives us 3 essential terms for today's lesson: supraglacial, subglacial, till. Now we are going to look at drumlins. Drumlins are smooth, elongated hills made of till. They often occur in groups called swarms. These landscapes are sometimes described as a basket of eggs because the hills look like a collection of smooth, oval shapes spread across the landscape. Drumlins are important because their shape can show the direction the ice was moving. A drumlin has 2 main ends. The staw side is the steep, blunt end. This faces the direction the ice came from. The lee side is the tapered, gentler slope. This points in the direction the ice was moving. So, if you look at a drumlin from above, the tapered end acts almost like an arrow showing the direction of ice flow. The slide gives the example of the Ards Peninsula in Northern Ireland, which has thousands of drumlins. Drumlins are useful evidence because they tell us not just that ice was present, but also the direction in which it moved. Let's ask a question. If the tapered end of a drumlin points east, what does that suggest about ice movement? Here's a model answer. It suggests that the ice was moving east because the lee side points in the direction of ice flow. Now let's look at glacial erratics. An erratic is a boulder that looks out of place. For example, imagine a huge block of granite sitting in an area where all the local bedrock is limestone. That would raise a question. How did the granite get there? The answer may be glacial transportation. A glacier can pick up a boulder from one location, carry it many kilometers, and then drop it when the ice melts. Erratics are very important evidence for geologists and geographers because the rock type can sometimes be traced back to its original source. If we know where the boulder came from and where it was dropped, we can reconstruct the path of the glacier. So erratics are like geological breadcrumbs. They show us the route taken by ancient ice. Let's ask a question. Why is the rock type of an erratic important? Here's a model answer. Because if the rock type is different from the local bedrock, geographers can trace where it came from and work out the direction the glacier traveled. Now let's apply what we have learned. The question is, if you found a terminal moraine in a valley today, but no glacier, what 3 things could you conclude about the history of that landscape? Think carefully. A terminal moraine is a ridge of till marking the furthest point reached by a glacier. So what does that tell us? First, it tells us the area was once covered by a glacier. Second, it tells us the glacier reached that specific point before retreating or melting. Third, it tells us the climate in the past must have been colder than it is today because conditions allowed ice to build up and move through that valley. Write those ideas as a short paragraph. Suggested sentence starter. The terminal moraine suggests that. You might have said, the area was once covered by a glacier. The glacier reached exactly that point before retreating or melting. The climate in the past was significantly colder than it is today, allowing ice to reach that latitude or altitude. That is a strong geographical answer because it uses the landform as evidence. It does not just describe the moraine. It interprets what the moraine tells us about past environments. This is an important exam skill, using physical evidence to reconstruct past conditions. To summarize today's lesson, glaciers transport material in 3 main ways. Supraglacial load is carried on top of the ice. Englacial load is carried inside the ice. Subglacial load is carried beneath the ice. When glaciers melt or lose energy, they deposit their load. This material is called till, and it is usually unsorted. Deposited till can form landforms such as moraines and drumlins. Erratics are large boulders transported and dropped by ice, often in areas with a different rock type. These features help geographers understand past glacial movement, past climate, and landscape history. Glacial deposition is not just ancient history. It helped shape the soils of places like East Anglia and the dramatic landscapes of upland areas such as the Lake District. In the next lesson, we will look at how human activity interacts with fragile glacial environments.